In this video, we're going to introduce the concept of verifying an identity. So as a quick reminder of what an identity is, an identity is an equation that is always true, regardless of the value of your variable or variables. An example of an equation that is an identity: 2 times the quantity x plus 5 is equal to 2x plus 10. Now, regardless of the value that I plug in for x, the left-hand side is going to be equal to the right-hand side. Now, if we turn it from left-hand side into right-hand side, this would be an example of the distributive property, whereas if we turned it from the right-hand side into the left-hand side, this would be an example of factoring a greatest common factor. To verify an identity, is not to do algebra as we typically do. To verify an identity is to start with either the left-hand side of an identity or start with the right-hand side of an identity, and through a series of algebraic or trigonometric steps, turn one side into the other. So working with only one side of the identity, use algebra or other tools to manipulate that side into the other side. To give you another example of an identity that we'll actually verify, I would like to verify the following identity. If I take two variables and I add them together and square them, and take the same two variables and subtract them and square that, and subtract the results, the result will always be equal to 4xy. Now, technically, you're allowed to start with either side. I'm going to have us start with the left-hand side. So LHS for left-hand side. As soon as I make this decision, I now know what my final answer is for this verification. My final answer is now the right-hand side. That is what I'm striving to get. So x plus y, quantity squared, minus x minus y, quantity squared, will be equal to. First thing I'm going to do is expand this square and expand this square. We'll call this x plus y times x plus y. And we'll call this x minus y times x minus y. Then, my second favorite four-letter F word, we're going to FOIL. When we FOIL, in both of these cases, the inner term and the outer term will be equal to each other. Oops. So the first one will be x squared plus 2xy plus y squared. The second one will be x squared minus 2xy plus y squared. Then we can distribute this minus sign. I guess we don't really need parentheses anymore. Not after we apply the distributive property. Guess we really didn't need them for the first set of parentheses anyway. And finally, we can combine any like terms that we see. The x squared minus x squared will cancel out, the y squared minus y squared will cancel out, and the 2xy plus 2xy will combine together to become 4xy. Now, this completes the verification because I arrived at the right-hand side. Now, typically, when you're working with an identity, as you go from step to step, it's a good idea to justify each of your steps. Back in geometry, this would have been referred to as a two-column proof. But just because you do something doesn't mean that you don't have to explain what you did. For example, at the first step, we applied the definition of what it means to be squared. So that's the definition of a second power, is to multiply something by itself. Then we expanded, or if you prefer, FOIL. Going from this step to the following step, we distributed the negative sign. So distribute. And finally, going from the second to last step to the last line, we combine like terms. My expectation is, as you're verifying identities, you will include a justification of every single step that you do. The reason that I insist that you include a justification is because I know that this thing equals this thing. And in order to do so, I know that this thing is equal to this, which is equal to this, which is equal to this, which is equal to this. I need to know why. The big important question to ask in mathematics is why. So with that in mind, in this section, we are going to be verifying trigonometric identities. It's the same as what we just saw on the previous page. The difference is that for trigonometric identities, that'll be identities with trigonometric functions. Now, if verifying a trigonometric identity was like building a house, then you would need to know all of the tools that you have access to, like hammering a nail, or wiring an electrical socket, or little things like that. Those little things we referred to in the previous chapter as, oh boy, hang on, spelling is hard, fundamental identities. There were 4 different categories of fundamental identities, and we have been expanding on that. So we had the reciprocal identities. The reciprocal identities let us know that the cosecant of an angle was the reciprocal of the sine of an angle, that the secant of an angle is 1 over the cosine of an angle, and that the cotangent of an angle is equal to 1 over the tangent of an angle. There were also the quotient identities, which is how we were able to express the tangent of an angle as a quotient of 2 other trigonometric functions, or the cotangent of an angle as a quotient of 2 trigonometric functions. We also had Pythagorean identities. And there were 3 of these. They were the sine squared of an angle plus the cosine squared of an angle is equal to 1. We also had tangent squared of an angle plus 1 is equal to the secant squared of an angle. And finally, 1 plus the cotangent squared of an angle is equal to the cosecant squared of an angle. Then we had our cofunction identities. Which involved complementary angles. I'm going to shorthand this. If alpha plus beta is equal to 90 degrees, or pi over 2 radians, then the sine of alpha is equal to the cosine of beta. The tangent of alpha is equal to the cotangent of beta, and the secant of alpha is equal to the cosecant of beta. And finally, we added to this in section 7.5 with our even and odd identities. Two of our trigonometric functions are even functions. Cosine of negative theta is the same as the cosine of theta, and the secant of negative theta is equal to the secant of theta. We say that these two functions are even. The other four are odd. The sine of negative theta is negative sine of theta. The tangent of negative theta is equal to the negative tangent of theta. The cotangent of negative theta is equal to the negative cotangent of theta. And the cosecant of negative theta is equal to the negative cosecant of theta. If you haven't already done so, either keep these identities handy or memorize them all.